I think there are basically two subparts for this P3B, if you didn't realize that. So I'll go to P3B here. So basically, part A and part B. So part A should be easier, and part B is the most difficult, okay? So you should definitely start from part A. Okay, so part A, the thing to do is very easy to understand. So basically a null pointer dereference. So what does it mean? So let's just try to run the original x86 code. Before that, let's just try to copy a user program. Let me borrow user program from here, which is called null. Oops, sorry. Sorry. Okay, good. So let me try to edit the makefile. Basically, just add a null here. Okay, so this program is called null. So this is the original version of x86. Sorry, I should have. Let's just go to this code to see what null does. Okay, so it's actually very simple. Yeah, actually I forked the process. That's fine. And here you set a pointer, and then the address is 0, right? And in Linux, when you set up a pointer to be 0, essentially just I think it's equivalent with assigning it to null, right? So null p is actually just the null pointer. However, if you dereference this null pointer in x86 in the original version, it's totally acceptable. No segmentation fault will be raised, which is very different from Linux, right? If in Linux you assign a null pointer, you have a null pointer and you try to dereference it, or you try to get the value from that pointer, you'll definitely get a seg fault, right? But in x86, it doesn't. So for this part A of P3B, you essentially want to have a raise exceptions or raise segmentation fault for the null pointer dereference. That's what we do here. So
why do you order the process to do this?
That's a good question. I think that I just directly copied from the test case. I think we can, as of now, I think we can just make it simpler.
Well, is it so that you don't kill your, like, it's just going to terminate that process? Is it so that you don't get, like, you can continue to run other things?
Yeah, I think that's correct. Okay, let's just try to write a.
Well, I think it's so that when it does eventually go ahead,
yeah.
it starts working.
Right. Okay, now let's just set it to 0. Okay, and then so now p is a null pointer. But if I try to print something, and we try to dereference p, let's see what happens. Nothing happens. Just some weird garbage, but definitely no exceptions. So I just try to print a. Sorry, in hex, it's simpler. Okay, just some looks like a random numbers, but actually these numbers are sort of meaningful when we proceed to the discussions. But as of now, you can just treat it as garbage. But definitely no exceptions raised. Okay, why is that? Now let's just take a look at the original x86 virtual memory layout. So I think in the x86 manual, probably we have similar diagrams. You can also look at the book, textbook, the manual. But as of now, I just simplify it. So okay, so here I said virtual memory layout. I particularly take a look at the user space. Okay, so essentially. So here's a low address, right? All the way up to high address. So this is, just do this, okay? And actually, when you look at the code, you'll see a macro called user top. User top, I think it's a followed by 4 zeros, which is 640 KB. Okay, so this is actually the whole address space for the user process. So user process can only live within this virtual address space, and definitely we have more higher addresses above user top, but that's for the kernel. And for this project, we don't need to care about the kernel memory. Okay, all we need to do is just within the user. Okay, so for the first page, we store code and data. Okay, so one page is in hex is 1 followed by 3 zeros. Okay, and for the second page, we store the stack. And in the old or original x86, the stack size is fixed. The maximum is just 1 page. Okay, instead of the modern Linux memory, right? It can grow, but in the original one, it doesn't grow. It's a fixed size of stack. It's just 1 page, but it just grows downwards. It just grows from here, from 2000 all the way down to 1000. It grows downwards. Yes, I should do like this. Okay. And above 2000, we have the heap. Okay, and heap will grow definitely, also in x86. Okay, so when you look at the proc.h, the PCB, you'll see a field called sz. This is very important for this project. You will, believe me, you will look at this great deal. So I think sz is simple for this original memory layout. You can just treat it as a bounds register for the heap, right? That's essentially what sz is for. The bounds register for the heap. Okay.
So the stack is the stack, is that what that arrow shows, like the stack going down?
Right. The stack, okay, basically, when it grows down, you can assume that the base register for stack, well, when you say base register, you mean the physical address, not the virtual address. But so when you translate this virtual address to the physical address, and that's the base register for the stack. Okay. And yeah, and the stack will grow, but it's the maximum is just 1 page. Okay, and here it's just a free, unallocated. Okay, this is the original memory layout. Okay, now let's go back to see what happens when we dereference a null pointer. So null pointer again is address at 0, right? And that's a virtual address, right? So essentially, you are accessing this 0. And it doesn't surprise us because you will not get a seg fault because this is mapped, right? It has something, which is the code and data. So when you try to dereference a null pointer at the original x86, you essentially just get something from the code and data. That's what that's the consequence of null pointer dereference. So to address or to resolve this issue, I think in the specification we say that, okay, since we will hit the code and data at 0, let's just try to have have 2 more pages, which is unallocated here. So now here, unmapped, which means free or unmapped or free. And code and data just starts from 2000. Okay. And now will be 3, right? And here it should be 4. So this is what we will do in the first part. We'll implement null pointer dereference, which means we will have the first 2 pages to be unmapped. If you do this way, then again, if you dereference 0 address, okay, it's unmapped. Now you will get a segment.
Is this the one that Linux does it?
I guess so. I'm not 100% sure, but I think so. Yeah. So what is segmentation fault? It's just when you try to access that virtual address, right? But it's just unmapped, or it's not the valid bit is 0, or the protect bit is 0, something like that. Specific bit is 0. So, but for one case, it's just unmapped. Right? But I don't think segmentation fault is all due to this unmapped. It can be like, again, I said, it's probably the protection bit is 0. Then you can still got a seg fault. But yeah, for this particular case, we just leave the first 2 pages unmapped, such that you can have a null pointer dereference. So, and for the second project, we want to, which is more challenging, because we now want to move this stack to the top. Okay, so yeah, it's hard to. So now we want to do it here. Okay, and there's no word like. Now, this is what we will do for the second part. Sorry. Okay, now things, so code and data will always be 1 page, so here will become 3. And because stack now grows downwards, so you have to also maintain the bounds register for stack, just like the bounds register for heap, which is size. Okay, you can just like whatever, like the top or just some name, put it into your PCB. That's very important, so that you will know that the bounds register.
Put it into what?
Sorry. The bounds register of the stack, you have to maintain this register as well.
I think like this is the
Yeah, SZ is originally a field in PCB. You can take a look at. So here, right, the first field, very first field. But the comment here is that the size of process memory, it applies to the original memory layout, but it no longer applies to our rearranged version, because SZ no longer can be the size of process memory, because you have extra pages up here, right? Its size is no longer the virtual memory size. It's so you have to basically add this portion as well. So there are a lot of corresponding consequences. So basically, every time you see SZ in the code, you have to think about it do I need to update that correspondingly? So basically, you can search. So this can be tricky because since we try to rearrange the whole memory layout, a lot of old assumptions made in XV6 may no longer hold in the new one. So you have to do the adjustment accordingly. So you can search for size. I think there are a lot.
Would you still recommend keeping size as the top of the heap and
I recommend
not
that.
making a new one? And
I recommend you can just use SZ as the bounds register for the heap and create a new bounds register for the stack. So
It's not really a register though, right? I mean, it's this member of this struct.
right. This file size don't just size, okay? So probably these two, don't worry about that. Okay, exec C definitely. I will talk about that in detail. So we use GDB to go through exec.c, which is very important. And there are a lot of things in proc.c. You have to do that. Okay, syscall.c also. Sysproc.c probably, and vm.c. Yeah, so basically vm.c, syscall.c, sysproc.c, proc.c, exec.c. These five you should especially take care of because again the assumptions changed, so you cannot. You have to make sure that it still applies to the current version. Okay, it looks simple, right? But actually, in terms of implementation, it's very challenging. The difficult things rise because sometimes it's really hard to debug. So if you do not have a good knowledge of what specific portion of the code, what is it doing, so that's the challenge. Some high level idea of what specific method does, then probably it's easier for you to debug. So, okay, this is some conceptual level of the project. Okay, now let's just try to go to see, probably not exact.c yet. I think let's just try to start looking at proc.c first. So, so I think we should start from user init. So if you still don't know what user init does, that's fine. So essentially, user init just creates the very first process. So as we know that processes are normally created by fork, right? Except for this, the very first process. This is very special, right? Because there's nothing to fork from. So we have to basically start from scratch for this. But other than that, for the following process, like shell or whatever you just basically fork. And that's simpler. So you have to create the first process. Creating process definitely involves the memory layout, right? So there are a couple of registers you have to take care of. For instance, like this guy, right? Size. You have to change it accordingly. And also the ESP, which is the stack pointer. Right, the stack, you have to maintain this guy. Okay, and EIP. So what is EIP? Right, the instruction, the CP, right? The count. Sorry, PC, the program counter or the instruction pointer. Right.
I have a question about what you're saying to change ESP and SCP. Is that specifically for the second part of this project?
Also for the first part. Right. Because you move it up by 2 pages, right?
So that's for the init code, for the actual first process?
Right. For the first process, you should also think about how you adjust the pointer.
Maybe this is key. When we're adding those extra 2 pages above it, so that means everything else is getting shifted up, but like so that limit that you size, even like on
So EIP should definitely change, right? Because
Right.
if you're still pointing to 0, that's
Then
unmapped,
that's
right?
the problem, and I get that. I'm just talking about the first part, I'm trying to get the dereferencing the null pointer, but like,
You mean the second part? Or
No, the first part.
first
No
part?
pointer.
So you want to change the stack point for the first part, then you change the
right,
second part.
that's what
then
I'm
you
trying
change
to confirm, because
Yeah.
I'm just trying to get the first part.
Okay.
it. Yes, but you're
Yeah.
going over
Yeah.
both pieces at once right now.
Okay, this, and then, okay, after the first process gets created, we'll try to create a new process, right, like the shell, which will use fork. So definitely you should take a look at fork. And very importantly is here, right? Because what fork does, essentially just copies, right? Including many important registers, that's fine. But the most important thing is it just copies the address space from its parent process, right? So it's copying the address space. Now address space changes, the layout changes, you should also update it correspondingly. So here, how does it copy the address space? It uses copy UVM. So this function, you definitely need to look at it. And let's try to.
If we set up the initial process to have the changed memory, why do we have to change it?
Oh, this is not for the initial part. I mean, not the initial process. This is like the process 2, PID 2.
Yeah,
It's because the stack will be different.
Okay, so let's take a look at. So I think it's at vm.c, copy UVM. See, so given a parent process, you basically create a copy, right? And you can see here, it's actually just a for loop. See, from 0 to size. So according to the old assumption, size is actually because it's contiguous, right? There's no gap, or it's contiguous, and so you can just directly from 0 to the size, and you do all that for every page size. That's totally fine. But right now, for part A, you should not start from 0, and for the second part, you should also include the stack copying, right? Because if this is just copying. This is just copying this chunk, right? But again, when you do fork, when you copy the address space, you should also copy the stack, right?
Oh, we can't start from I of 0. We have to start from I of
Right.
0x2000.
Right. So there are a lot of changes, so you have to take care of it. Okay, this is just copy UVM. And I think this will look fine. Okay, now we're talking about fork, right? Okay. So after we fork a process, what we do?
Copies everything, puts the new name program into the name.
No, I didn't ask you about what's following in the what I mean. I was asking what we do after we fork. Exactly, we'll do exec. So that's a challenging part. So the code of exec is not in proc.c. It has got a separate file called exec.c. So we'll definitely look at this. So to look at this in detail, we just use our old friend GDB. Okay, so let me allow to make sure that I think I should set up yeah, here. So let's make query GDB. Okay, and now here I think it's demos. X6, okay, GDB. Okay, let's just break at exec. Okay, dots. Yeah, exec. Okay. Now, I think I need to open another such that we can look at the code.
Is that why your other code?
Sorry?
Oh, never mind. Now I'm confusing the two.
Uh, demos. So let's just open this file. Okay. Okay. So we break it into exec. You can see exec is actually a method. It takes in two arguments. One is called path. The other is argv. So here path is a string called init, which means we are executing the very first process. And there are some the arguments here. So I think I will just break at 26. Okay, line 26 is here. Okay, we'll try from here. So for line 26, we'll check ELF header. Anyone knows what is ELF header?
You can define, it's kind of a dash that defines the code file in some way.
So you can simply think it as a header of the executable. So basically, when you have a user program, right, you compile it, and then you will get executable, which is a binary file. And at the very beginning of that binary file, it's the ELF header, and it stores some useful information. And actually, at the very first 4 bytes, the very first 4 bytes of this header, it's actually storing a magic number, such that the kernel will recognize this and then execute it. So we'll go through that.
You said think of it as the beginning of the binary file, like for the execution.
Right.
So like a code and set of data.
Right. Mm-hmm. So let's just take a look at, so I think all the executables of the user program resides in FS, the full FS directory. You see they are all executables except for the readme, but that's fine. Let's just take a look at init, okay? But if you just cat it, it just got a bunch of garbage because it's binary file. We can use xxd. I think I introduced this to you guys earlier, but it's just dumping the binary file into hex. But because there's a lot, so I use less. So you can see, this is the header. This is the 4 bytes, the very first 4 bytes, which corresponds to this 4 bytes. This is actually the magic number. So as long as exec.c see this magic number, it will say, okay, I found this magic number matching with this binary file, and then I assume this is the correct binary file I will run. And then later I will load the remaining portion to the virtual memory, and then do the execution. Okay. And let's take a look at, let's go on to C. Sorry. Let's go on the GDB here. So C. So this line 26. So read I essentially just similar to read, but it's kind of a more lower level read. It's not the real system call, but it's more lower level for kernel, and essentially read the ELF. So IP essentially, like, you can regard it as a file descriptor and read into the data structure of ELF. And how many bytes, which is size of ELF, you can just try to print it. 52. So basically the header is only taking 52 bytes, the header. And you just load the first 52 bytes into this struct. Okay. And after that, you can just print ELF. So ELF here is actually just a data structure. We store the header. You can see the first field is called magic. And just try to print elf.magic. But it's actually the hex. It's decimal. You can convert it to hex by /x. Does it look similar? 464C457F. Looks like reversed, right? 464C457F. The reason being, it's little endian, so it's reversed. Okay, so yeah, that's the magic number. And then you can see, oops, sorry, see line 28, see? If this magic number matches with, you can look at the magic, it's, believe me, it's definitely this number, but yeah, okay, it's matching. Now I can go on to set up everything and then load the remaining portion of the code and data to the main memory. Okay, so this is just set up the page directory. We don't need to care about this. Okay, for this line, we just because there's nothing in the heap, so size is 0, right? The bounds register. And then we just try to, oh, sorry. Because we haven't loaded anything yet, right? Previously, read_i is just loading the header. It's not the program itself. It's just like a header with a couple of information here. It's sorry. Go ahead.
Is the header discarded then? It's not saved into the code section of the process?
No. Okay, and then because in the header we have a couple of information like some flags or some size. Yeah, we just use this as like following when we populate the virtual memory, some information here, but we don't load it into the main memory. So basically, we will start from 0, right? Because the old version starts from 0, the virtual address space. And then again, so we read_i, right? Read_i is just a load from the file, the binary file system on the disk to the memory.
So just taking a step back here, what we're reading, is this in fork or is this after fork or is
Oh, this is in exec.
Exact.
Exec.c. We're looking at exec.c.
Okay, so it's actually loading, it's looking for like the compiled file.
Right.
Can you remind me of just how you started up this GDB session? Was this with the Q email?
Yeah,
Oh, this was in
on
the
one.
same session.
So
where you loaded
basically,
the GDB.
so one terminal you type make qemu
Okay,
GDB, and the other you type GDB. But you have to make sure that you are at the same machine, and also you have to set up the
Start this one first.
.gdb init file correspondingly.
We walked through it in the one video.
Yeah.
That's the easiest way to just do it. It's just kind of do it when you're opening it.
Okay, so read_i is just a load from disk to the virtual memory, and then
But you're saying you don't care about the size here for 35 SC?
Not yet because we haven't gotten past the heap.
right. This is
We're gonna-
I'm just going through the original
But
version.
wouldn't
Oh,
we have
okay,
to
that's fine.
know
Yeah.
the difference? Because this is basically saying let's start loading into 0.
Right.
Right?
So you don't want to read into 0 now, you want to read 2 pages up.
Yeah.
So
Something
we
like
do
that.
care about it.
Yes.
Just want to make sure it's like 4. So that's all.
Okay, now we come to another important portion, which is so let's go back to line 43. So where are we? So we are here. These are just some sanity checks to make sure the size does not. Yeah. Okay, this is very important. It says alloc UVM. The reason is that now we are essentially trying to. Okay, so read_i essentially just put the information to this data structure called ph, right? but it's not in the virtual memory yet. So you can just print ph. So yeah, ph is a data structure that stores some information like the file size, which is 2877, right? And also the virtual memory starts from 0. But we haven't really populate the virtual address yet, virtual address space yet. The reason is that before loading, we have to allocate allocate the memory, right? Otherwise, we cannot load it. So we have to use alloc UVM to create to allocate some memory, so that the virtual address space from 0 to like 1 page or 2 page will get mapped to the physical address space. So that's what alloc UVM does. So let's go a step into this line 43. So now we are in alloc UVM. So you can see the argument here. So this is the page directory address, that's fine. And we just care about old size and new size. So old size, it says, starts from 0 to, grows from 0, which is nothing, to this many bytes, which is corresponding to memory size, because we want to allocate this many memories such that we can load our code and data, right, into the virtual memory. And here we does some bunch of sanity check to make sure that size does not grow over the user top. That's totally fine. And if the new size is smaller, which means we're shrinking, right? If new size is smaller, then basically we'll deallocate or free the memory. But as of now, we just grow the memory, which definitely will be new size greater than old size. Okay, and here what does G ground up? So how to read that? Okay, so it's P ground up. So this is a macro function. It's actually doing some round up things. So such that the new address is page aligned. So just make sure that it's page aligned. The reason is that you can see old size is 0. It's already page aligned. So I think this does nothing. If somehow your old size is not page aligned, you will call this ground up and make sure it's page aligned. So always starts from the page aligned and then grow up the address. And here we just loop through for each byte, right? This is we allocate a real physical address and then do the mapping. Right? Make sure it doesn't fail. If calloc returns 0, then it fails. But okay, it doesn't fail, and then we just clear all the bits in the allocated memory to be 0. Okay, and here we basically say, hey, I have already allocated some memory in physical memory. Now I want to map the physical memory to our virtual memory. That's basically what we do for map pages. With some protection bits. And that's it. Because we have only one, it's actually less than 1 page, right? New size is, I think I'm printing hex. New size is, this is less than 1,000 in hex. So it's, because 1 page is 0x1000. So it's less than that, so it's just 1 iteration. Okay, so now we'll go back. Okay, so now we have finished alloc UVM, right? And then, okay, remember alloc UVM will return size. So originally size is 0, right? So let's see what size is now. X. that makes sense, right? Because you allocated this many bytes of memory. So which is so essentially, I think alloc UVM will just return. Alloc UVM will. I think it will return this number. Okay. Now, what's the next step? We're just allocating the memory, and then to populate that, right? With load UVM. So let's just step into this load UVM. It's also at vm.c. Okay. So both load UVM and alloc UVM are in kernel/vm.c. So for load UVM, the start address is from 0, and the size is 2877. So size, right? So I think this size is directly from this guy, right? Load UVM here. Yeah, because the file size is 2877, so we want to populate the memory from 0 to 2877. And here, previously, when we do allocate, yeah, this one is bigger than this. That makes sense. Otherwise, it will overflow. So we are actually allocating more memory than needed. But, yeah. Okay, so again, we just for each byte, right, from 0 to size, which is 2877. We basically so walk page directory is essentially just a translation from the virtual address space to the PTE. So address is the virtual address, right? From 0. Address is 0. I is from 0 to size, so they are virtual address. We just use our page table to get the PTE. And then we do the translation. We get the PTE, then we get the physical address, right? And after we get the physical address, and then we read I. So we still always use read I to really populate the content to that address. Does that make sense? So we cannot directly read I to the VA, right? Because VA is virtual. Go ahead. So walk page directory, essentially, you can treat it as you got a virtual address, and then from walk directory, you will get the PTE. You look up the page table, and then you get PTE, page table entry. And with PTE, you'll get the physical address. And we'll read the stuff to the physical address, right? Because virtual address is virtual. You cannot do the virtual things. You would essentially populate the stuff into the physical address, right? Okay.
So this is actually populating it even though it's called read?
Sorry?
It's just confusing that it's called read, but then you're saying it's populating the data?
So essentially, it's reading from the disk to the physical address. Not reading from the physical address yet. Yeah. Or you can say it's load. So that's why it's loading there. Yeah. Okay, since everything makes sense, we'll return. Now where are we? We are at 9:36. Okay, yeah, this loop is over. Then we'll loop over. I think this is just one loop. But after all, this loop is as indicated by the comment. It's just loading the program into the memory, the code and stack. I'm sorry, the code and the data, which is just one page, right?
And the virtual address is
From 0 for this.
ph.va that we're loading into ph with that read I.
So,
Because that's what we pass into load UVM.
right, I think this is 0. We can check ph.va. that's 0.
That also is cheap.
Good. Okay. Okay. Now we are finished with this part. Basically, so we have populated with this, right? Now, because it's the old one, so we will then populate stack. They're contiguous in the. Oh yeah, I removed. Yeah, I should have done that. But yeah, remember that. Now let's try to populate a stack. So we'll go to here. Allocate a new page stack at the next page boundary, right? Because just one page for the stack for the old one. You should update that accordingly.
So everything you did until now was just loading in the code?
Right. Yeah. Okay. So let's go back to the GDB. I know it's a bit tedious, but I mean, okay. Okay, I think we are at line 52. It's line 52. Okay, now let's take a look at what's the value of size. Okay, again, doesn't change. Right. Okay, now we want to round up the size such that size is page aligned. Why we do that? Right, because previously size is from you load from 0 to this number B4C to store the code and data, right? But you don't want to use the rest of. You want to start from the new page to store your stack. That's why you want to round up the size.
So you just leave.
Right, exactly. You just leave that empty, but it's allocated. It's just not populated. Well, no, I think it's still unallocated because because we
Those PTEs haven't been initialized.
I mean, we called Alec.
yeah when we call alloc UVM,
We didn't alloc for the whole page size. We only alloced for the actual data size, the code size.
yeah, not quite.
It was a little bit more than the code size, right?
Right. It was the
Because we
0x.
Yeah.
4B.
See, we alloc UVM. The size is 2.
Yeah, it wasn't a full page.
Right. It's not 4096. So again, there are some pages, some bytes that are allocated. But yeah.
Where did that 2892 come from? Is that just because we know the size of the first program?
I think this number is directly from the alloc UVM, which is here. So ph.va is 0, right? And ph.mem size. It's just mem size, this guy.
But even if we never allocated it, that the space in physical memory on the top of that to the top of the next page will never be used, right? Because the physical memory is also segmented by pages.
Right.
So Alec won't get it anyway.
Okay. Now we want to round up to the page so that it's page aligned, and then let's take a look at size again. See, now size is page aligned. It's 1 page. Okay. Now again, we'll do alloc UVM again, right? This time the old is size is 1 page, and new is 1 page plus 1 page, which is 2 page, right? Because we want to allocate 1 page size for the stack. That makes sense. I'll now go to this. And the returned value is the new size. Now I think size should be 2000, right? Okay. Okay. After we allocate this new page, we will assign SP. We'll assign size to SP. So what is SP? It's just stack pointer, because even for the old XV6 memory layout, the stack is still growing downwards, right? So the stack pointer should start from. I'll just write down the old. So start from 0. The first page is code as data, right? And somehow we just allocate here like trace and something. And now we round up so that size is pointing here, right? And now we call alloc UVM again, which will grow one more page. There's 2000. Now size will come here. Sense. And this page is for stack, right? Now stack should grow downwards, which means SP, the stack pointer should start from here. That's why I assign SP to be SE. And then, okay, so what's the first content to put into the stack? Anyone has an idea? So in your user program, you always have a main function. And you have RC, right? And then char star something like this, right? So you have already loaded this instructions or code into this segment. And then you want to populate a stack. So the first thing you want to do is basically put these arguments into stack. So I think I also mentioned that in previous discussions about the x86 function call. Calling convention, right? So main is just a function. So every time you call a function, you will put some arguments into stack, right? And you will just push them to stack in a reverse order, right? So basically, you will push this guy first. However, this is like how many arguments are there is unknown. Well, I mean, yeah, actually it's determined by RC, right? So you have to basically push, zoom in. So stack, zoom in. Stack. So SP starts from here, it goes downwards. So the first thing you want to push to stack is suppose I push to here. Say argc equals 2, for example. Then you should push rb1, right? And then you push rb0.
Like if you're in the middle of this one?
Yeah, because every time I push it this way, right? Every time I push, I will move it down. So
You're just leaving room for it.
okay, and then we push the address of RB, the address of RB itself, and then we push RC. And finally, we push the return address. So that's what it does. So
Does that mean stack is growing up in that scenario? Or like, should it be actually going below?
It's growing down if we're getting like pushed down.
We're not actually like moving all that down physically. Does that, okay, pushing them on the stack like that, does that say correspond to like where in physical memory, like according to what you have on the left? Or is that different?
what's gonna be at OX 2000 and what's gonna be at
Yeah.
OX 1999?
So say the next one should be 1FC.
Okay.
This guy should be,
Is that return?
yeah, I think should be the return address. Did I think it virtually?
Let's pull up the code. Is it actually?
I'm not, yeah.
Because it looks like it goes from argv0.
Let's just try to look at it, what it does here. So,
It starts argv of 0.
so here it uses another array called uStack. And then, so this is the return address, and this is argc. So yeah, probably. I think probably I got a reverse way. I think.
Is it still at order, but why would it push it down? Wouldn't it just fill in those
It'll
locations?
just fill in the
So the stack is going downwards, right?
Right.
Yeah.
So
So
first
when
they
it
just push on the
saves-
return address and then push on RC and then push on RV.
sorry. Yeah, that's correct. I got confused.
Even the coding
So
is
yeah,
really
it's because it's going downwards, so it's really. So okay, so here is what we do. So when we say we grow down, it means the first is here, right? So the first one should be, yeah, correct. So this one should be RV2, oh, RV1, and here it should be
Is it really putting RV1 and RV0 in, or is it just putting the pointer to RV?
Yeah, it should be the pointer chart because arg1 itself is a string, so it's actually yeah you can take a start here. I think it's so and then RC and then the returns. So okay. So when you push stack here, essentially you do this way. You push it this way so that it's grown downwards, not this way. So yeah, so that makes sense. So the first guy you push is always the last here. So you push this way and you got populated here. Yeah, it's very confusing and yeah, that's correct. And definitely it should be consistent with here. And you can see here in the code it says uStack 0. So uStack. So the first element is the return address, and then it's the argc, RV, etc. Right? And the index is 0, 1, 2. And here for copy out, essentially just I think it's copying the stack to this to populate this the stack in the virtual memory. So if you do this way, then 0 is a lower index, right? Lower index corresponding to lower index here. So and this is higher index, so this is consistent. It's low.
Starting from once we've moved SP down to where return address will be. So we're populating.
And here is low. Here's high. It can be very confusing, but yeah, because it's going down.
We
How
moved
could a
SP
high index
from-
possibly be at where the stack pointer starts?
Sorry?
How could the high index possibly be at the top when it's going down?
I think it's after we've already
moved it.
decremented SP down.
SP gets decremented.
Right.
there,
Every
and then
time
can
you
copy it.
push an argument, the SP will go down. So every time you push a new,
Yeah, but that means that your numbers on your, you'd have to know a finite number at the very top. Like you'd have 99, 98, 97, 96. How could you possibly know?
Because RC, it says right there SP, it's
So you
3
start
plus
with SP
RC
equal
plus
to
1.
SC, and then you decrement SP before assigning that value.
In row 73.
so, yeah. So you have already pushed SP down all the way down.
We're not really saving them like one at a time. We decrement, we figure out how many we have, we decrement SP all the way down, and then we populate that whole chunk together from SP up to the line.
So can you just write the minus equals?
Mm-hmm.
Does that mean
You
that you
remember you said
decrement it after you
do
do
you
that
have it all in
whole
one chunk?
calculation? Or before?
So line 73 should be equivalent to SP assigned to SP minus 3 plus RC plus 1 times.
Oh,
So it is the right side
okay.
first.
You do this first and then.
What's the SP ampersand equal?
Oh,
Something
that's a
three.
good question. So line 62. So this is essentially make sure that it's every 4 bytes. So because it's a string, right? So line 61 has like string length plus 1. So you cannot guarantee that after SP minus this number, it's still a multiple of 4. SP has to be always a multiple of 4. The reason being the size of integer is 4. You cannot have like my SP is not multiple of 4, then everything will be in a mess. Does that
So
make sense?
I'm assuming like this is the okay. So when we change the way the stack grows, we're gonna need to change all these places where we're setting SP.
Right.
Right?
Yeah.
But we're gonna be
We're gonna start SP from the top, and then keep.
SP equal SZ, set SP.
So that's gonna be the difference. Instead of setting it equal to SZ, we have to set it to the top, and then we have to track the.
So
I mean,
the same
I'm
direction.
drawing
At least
down
it's in the
then.
same direction. Yeah, we don't just switch the direction of
Oh,
it growing.
Okay.
So the
It's just a different
RC1 is in index 0 of the stack. I think I missed that part. Or is it
Sorry,
index-
RC.
RC1, like, is the stack just indexed?
Yeah, this is index.
The U stack isn't
You use that index.
this U stack that we do
Right.
just to kind of build it up temporarily for what we're gonna save.
No, I know, but after it's copied out, is it indexed like 0, 1, 2 from the top? Like where RC of 1 is in that diagram, is that index 0? No, in this. Is this
Our
index
vehicle?
0?
No,
1,
No,
2?
no,
that's
no.
the highest.
This is
Okay.
highest index because this is low, this is high.
And it's because of the memory location and how like C would then store data, right? 'Cause
Right.
otherwise you'd have to insert each one individually the opposite way.
Yeah.
So it's just a way to say, okay, I have this pointer here, now I have this pointer here. I'm gonna go down here because I wanna do this amount of memory. But if I put it here, I'd have to do it individually each every one. But because of C and I'm growing memory in this direction, but I'm actually doing it in this
So-
direction, I just chunk it over.
Right.
It says intentional as But then why would you do it a different
So
way?
you know but you know the index because you know the size of the stack.
The size of the RG.
Yes.
It makes sense to use the
RC is just basically.
No, but the stack will keep growing after this layer, right?
Yeah. But this is just for loading the argument for main. You have definitely more, but that's not for the main.
So maybe I shouldn't even think of the stack as being indexed, it's just.
Right, but my point is that then
Yeah, it's not, it's just address.
Yeah, just that.
Just an address and a stack, yeah.
So it's, don't make that.
Yeah, I think it looks very confusing, but if you spend some time trying to use GDB to go through this, probably you have a better sense. But because of time, so probably I would not go through this code in very details. But I think this is just like spend half an hour to track this. You have a better sense. Another issue here is that why are we assigning this FFFF to the return address? Not exactly. So where are we? We're at exec, right? what will exec return?
Oh no.
Right, that's the trick here. So since exec will never return if it succeed, then we just put a fake address PC here. But what if the stack? So the EIP, right? EIP will finally go to this return address, and EIP when it hit this address, it dereference it. It basically set false. And then it will trap, right? A trap handler will see, oh, there is a trap, and oh, there's a set fault, so I'll just kill this process. So that's what we do here. Like a hack, but
I don't think C is known for
I don't know. Actually, I don't know if in Linux it's really doing this way, but in x86 it's just like some hacking. But yeah. Oh.
So does x86 grow the stack if you run out of a page?
I think it just set false because in like the allocation.
So in the older version, the maximum size of stack is just one page. If it grows down to the code data, it just reads garbage.
So can we have a max size of one page? It's just at the top now.
So the reason we do this rearrangement is that we want to allow the stack to grow.
Wait, so the theoretically the stack starts to overwrite the code?
Sorry?
The stack starts to overwrite the code?
Yeah, it will hit it. If you do some heavy recursion, for instance.
Do we just stop that from happening? So do we need to be comparing the stack pointer with the heap pointer all the time?
For the second part, you have to care about that.
But I'm
But
saying
that's
like XV6 as it is right now,
But there's no
apparently
main plan.
doesn't care, it'll just overwrite.
You like computer science.
Huh?
Kill the
This,
process.
yeah, in current old version of x86, we
But
don't
that
have
can
this
build
handle.
up, so once that happens.
Yeah, if you do, you can have a try to
Yeah,
do
we
like
do
need to
heavy
top of
recursion, then
and
you
make
get.
sure it doesn't affect the stack.
I don't think you will get that for either because
So does it- I'm saying how it works now, is with that fixed stack, it's written down.
You guys have a stack that's just like.
I think it stops it, right?
Actually just that.
I don't try that.
I don't know.
Yeah, probably will stop it, but
But so
Oh, you do?
in our program, if they meet each other the stack technique, should we just kill
Yes,
the
it's
process?
prevented.
actually, we have to make sure that there are like 5 pages gap between them. It's
At all
mentioned.
times? Oh, okay.
It's mentioned in the
Sorry.
instructions. Okay.
5 whole pages of it.
Yeah, the 5 unallocated pages.
So we have to,
The DMZ.
we're gonna have to keep adding space to the process, but I know the process has a fixed amount of space.
Right, I will talk about in details later. Okay, so I think I finished talking about exec.c. So I think another code you should look at is vm.c just now because I looked at load UVM and alloc UVM. They're all in alloc.c, vm.c. You should definitely try to modify that. And also copy of UVM, right? Alloc, oops, 8 o'clock.
Oh, no. No, everything's shut off.
It's 6.
And
It's unnecessary.
I know, we're here.
Really?
What do they keep those stupid lights going on
That seems like
But our projector needs
an
to
easier front to pick.
Are we gonna have a chance to go over like the init code stuff? Because that's like still.
Okay, init code. You mean the the user init?
Right, because that's like where I'm still like really struggling to get my program to work. Like I'm not even getting to exec yet, so
Yeah.
I really just need some help.
Yeah, I can personally do that for you
I mean, I
because
need to figure out how to
I mean because
not move the init code, but move everything else.
Can you actually take it in like a meaningful chunk for A, or do you kind of have to do it in all of the places?
You can move the kernel panic slightly further along, but it'll still kernel panic until you get like all the pieces.
Okay.
That's
So
at least
the
what
whole
I'm
thing
seeing.
before trying to run it.
Well, I mean, the reason I ask is that, right? Like,
Yeah.
generally, you're supposed to do it incrementally.
But I
Is
think the
there a
only
way
thing you
to
could do would be
actually do it
GDP.
incrementally?
Well, the first increment is null.
Yes.
No, but within part A, is there a way to increment within part A? Or is it all or nothing?
I think it's all.
It's all or
Okay.
nothing.
Part one of.
You
part
could
two.
GDP through it, I guess,
Yeah,
and see like where does it fail, but
Yeah. I'm not mad at you.
like none of it's going to run.
Part A and part B.
Part A,
Part
part B.
two, I don't think 3D2 or 3DB is
CS
very incremental
537
either.
-2,
Yeah, not really.
P3B.
I'm happy with it because I hate testing my code as I go.
I usually don't, but I hate it when like nothing works and I have no way of seeing what's wrong.
I can see that I set my instruction.
Well, I know, but it's like, how do I print all of memory and the page table to know where stuff is?
Put it into a file and then use control F.
Yeah, it's like I've been trying to decide, do I need to write a function that dumps all, like, the whole page table and tries to label where everything is? But I probably won't be able to make that work.
Well, right, the question then is like, is it the same or do you need it in multiple places?
You can't run that function because
Right,
Right, it doesn't even like get to.
yeah,
I don't think
think
right,
you can
right,
do
no,
I
that.
think if you
Right,
could
you
do
do
that, I think hackers would have a lot easier time.
Okay. So we looked at alloc UVM, right? And then we look at load UVM. Oh, okay, by the way, so I think load UVM will only be called once, which is just at loading the data and code. After that, load UVM will never be called again. So yeah, this is
Like
just a
only for
reminder.
User in it,
No, I think it's like
once per fork.
Yeah, once exact, because it's in exact.c, right? So every time you have a new process, you do that. Because each process has different code and code and data, right? So you have to load it, but just once for each process. But copy UVM,
that's like 4, isn't it?
yeah, exactly. That's in fork. I think it's only also once. Yeah, for one process. Yes. Yeah, I've mentioned that before, right? Just now. To also copy the stack. Right? Okay. Yeah, I remember I talked about it. Okay. So I think that's basically for vm.c. No, not yet. So proc.c. Okay. So another important piece, which is probably Natalie just mentioned. What if we collide between stack and heap? So just because I have that. So here you have to make sure that there are greater or equal to 5 pages as a gap. Another thing is that we have to make sure that stack will grow, right? But normally, the first stack we allocate is just 1 page. So put it here, we allocate 1 page. But how are we going to know that, oh, this is not enough, I have to allocate the other page? What do we do when we grow? Okay. Okay, so let me ask you a question first. When do we grow SZ? When do we grow the heap? Exactly. So when you call basically malloc, right? And you will grow SZ. But we don't have a system call or function to grow the stack. Stack should ideally be automatically growing as long as there's not enough space, right? Then how are we trigger this? So the trick is that, again, seg fault or page fault. So with the help of trap handler. So you should basically add another exception in the trap.c, the trap handler. Every time your stack encounters a seg fault, you will try to grow the stack by 1 page.
So does that mean
Does that
we're
make
growing
sense?
it up towards user top? Or,
No, grow down.
okay, so we will never grow up towards user
Correct.
top. So what is between stack and user top? Nothing?
It's not,
Or is it?
That's the top.
This
of
is
the
stack.
Oh,
This is stack.
okay.
It's growing downwards.
Oh.
Yeah.
So could you say that again? Every time we have to add a trap handler.
So basically, every time you have you encounter a seg fault, which is handled. So
So in the
let me
segfault
show you.
handler, we have to add
So you can take a look at
trap.
trap.c. So there are a lot of Ks, right? So switch. This is the trap number. So if trap number is 64, it's a system call, right? And this is, I think, this is timer interrupt. Okay, so here's the default. So I think seg fault or page fault, which is interchangeably used in x86, is the number is 14.
14.
Yeah, 14.
Had a
So
lot
you
of
can add a
14.
case. Trap is 14. Then you'll basically try to grow the stack by 1 page. Every time 1 page.
you said 14 was a page fault or a seg fault in x86?
So in x86 they're the same.
What?
They're the same, that a
Yeah,
seg fault and a page fault are the same thing.
Yeah.
Okay.
So, but you have to also notice that when you try to grow 1 page, you have to make sure it's not violating the 5-page
Right,
gap.
that's right.
So if it's violating, then you just don't create that page. Just throw the seg fault. Yeah.
Do we also need to do something for like malloc?
Exactly. Again, so when you grow heap from below, you have to also make sure the gap is also greater than 5 pages. So there are a lot of things to do. So again, the code in when you allocate the memory, the heap, when you grow the heap, is actually at proc.c called allocproc. Oh no, not allocproc. Called growproc. So it's here. So it's just growing the process's memory. So it's actually just growing as z.
So basically anytime we're increasing SC, we just need to make sure we're still.
Right. Yeah.
So, I have a question about if the program seg faults, when it's trying to grow the stack, like you initialize a new variable or something, it'll seg fault because it tries to initialize it to a memory outside of the stack.
Mhm.
And then we give it a new
Trap
page.
handler.
Trap handler, give it a new page.
Mhm.
When it goes back, will it try that again? Like, does it rerun the line that?
That's what traps does, right? The last step
Okay.
after you return from trap, you retry the instruction.
I can't remember.
I mean, it'll do
It's
it.
in the
So
test.
it'll retry
It's in
until
the
we go to
exam,
the
so
Right, it'll retry it. Okay.
yeah, that's in the exam. That's by the way.
Good. Bye.
next.
Will I get tomorrow?
That when I trap fails, or
How a trap handler works, it retries
It
the thing
retries
that's trapped. So that line gets tried.
So just to clarify with this new trap handler, this trap handler is specific to this situation
Right.
where the stack.
Right, only stack. Mhm.
Okay, so not when the heap, like when the heap, like the grow prop,
We have to modify the
is that's just gonna throw like. a
Oh, so if the user write a program that tries to access, so when it's growing the because if it's in the heap, then it
You're saying grow prop, this is basically when you're growing.
So we.
yeah grow proc. This is just for growing heap,
So
but
will we just throw, I mean, do we even need to throw anything, or do we just return -1 and then it does whatever it's gonna do? Is returning -1 is a failure.
If it tries to make it less than 5
Like,
page sizes in no man's land, then do we have to?
Like,
throw
are we
an error?
supposed to implement some new kind of handler for that, or do you just return -1 and like whatever thing is checking its return code will throw some kind of trap and
What happens when you
Well, that-
return -1 from program?
I think it's
I mean failure. Like,
failure. It's not. It will not raise exceptions. I think it's just the system call just fails. It will not raise exceptions. I think.
I mean,
So
so,
system
Like,
call
do we
fails, it
need
kills
to
the
raise
process, right?
exceptions when we modify this?
You mean when the gap is smaller than
Yeah.
5 pages?
like, is that
Unexpected
part?
behavior is just to kill the process, right?
I think.
Like, is that part of this new special exception, or is that only for the stack?
It looks like some of the traps in the maybe just routing it.
I know.
Yeah, because if the trap no is the timer one we yield, and it's some crappy.
I'm not 100% sure if we need to.
Says we just need to maintain it, so I'd assume we
You-
exit -1. It dies.
I mean, I feel like I'm fine with just returning -1, like do the same thing it does in any other scenarios.
Just put it as a note of a place where you potentially will have to change.
Yeah, I will double check that to see if you just return -1 or just have raise another.
And then I guess similarly, if we're growing the stack backwards, if it turns out we can't grow the stack backwards, what are we supposed to do? So
Yeah.
end of the kill.
Okay, so I think it does it for you. In that second part of
That's
the
true.
That's what he was saying.
But it's not going to be trap number 14. It's going to be.
It will be.
There's
It's
still
trap
trap
number
14, yeah.
the default.
Yeah.
And then
We're
if-
adding, we're enhancing the page fault
Okay. Okay.
trap.
So it's
Handler.
still going to be in 14.
It's still a page fault.
But
We're just saying, okay, page faulted, but now
This
we're
is
gonna add a page,
but it's a
then it's
special
fine.
kind of page call. Okay.
Page fault where we can add a
So we're
page
not adding
fault.
a new trap number.
No
Oh,
new
oh.
trap number.
So it's already in trap 14, that's not just in the default.
I think it might be the default because that's the one I'm getting. That message, that default message is the same message I'm getting for trap 14. But I think you will just have to add the case and kind of handle it special.
Okay. Another tiny thing is,
Oh, yeah.
as I mentioned, you also need to care about syscall. But since for this project we didn't write syscalls, right? But why are we gonna care about it? The reason is again size, because I just mentioned size. According to the old assumptions, size is from 0 to size is the contiguous thing you need to care about. But right now we have like two separate chunks of regions, right? So you have to take care of this. The reason, and for especially in syscall.c, there are a lot of boundary checkings. Every time you remember when you create a syscall and you have an argument to pass from user stack to kernel stack, before that you use either argpointer or argint, right? Argint and argpointer essentially just checks the address you throw in, make sure that it's valid, right? If it's not valid, that system call returns -1. Otherwise, it does the real thing. Again, here we also need to do the checking, but the checking becomes different because originally it just checks it, make sure that it falls within that contiguous range, right? But now we have two separate ranges, so you have to check if it falls in either of this range instead of just one. So you have to make sure. So the checking thing happening like at fetch int, right? So this is like the checking what I mentioned. Like this is the address I got from user space, right? And I have to make sure that it's not greater than size. And also because I take int, right? Integer, I have to take 4 bytes, right? So when it adds 4, it has to be smaller or greater than, smaller or equal to size. Otherwise, you return -1, right? Also, like fetch string. Argint is fine because argint just calls fetch int. Argpointer, yeah, here like it always uses proc size, right? Proc.size. Every time it uses proc.size, we have to be careful. And also
So
arg
they
string.
could be in the heap or the stack.
Right.
Would we know, or like, do we have any know if we're specifically?
You don't know. You just make sure it's either in yeah, either in stack or heap. Also arc string. So I think there's a lot of work to do and scatters everywhere. I'm sorry about that, but yeah, but before doing that, you have to make sure that you have a very clear, high-level conceptual idea of what you should do. So